Hi, everyone. Can you hear me? Okay. Okay, great. Just wanted to check. Thank you all for having me. And I'm very happy to be here. So maybe I'll start by saying a few words about myself. So I'm Angel. I'm from Simon Fraser University, which is actually located maybe roughly 30 minutes away from downtown. And my interest is in connecting language and 3D representations. And I'm interested in helping to build helpful AI assistants who can help you in the house. And because of this interest, I'm also very interested in having large-scale interactive environments. So here's just some pictures of what I think of robots that can help us around the house. Maybe you have a little robot that can help you vacuum the floor or maybe serve you breakfast. And more recently, there's an effort so this is actually also a kind of rearrangement where we have the robot want to move one object from one position to another. So here we want to move the stuffed animal from the chair to the sofa. And yeah, and so here's just a little video of this stretch robot doing that. Just move my stuff. Okay, but how do we get to such intelligent home robots? I think this is something that will take a lot of people's efforts from different communities, robotics, vision, and I also think in language, because we want to also communicate with our robots using language. And I myself have done a lot of work in developing different frameworks and also benchmarks. So I will start with that. And what we want to do is we want to be able to make it easy for everyone to work in this area of robotics, not just a select few people who can have specialized skills. And in addition, we want to make it easy for not just roboticists to explore how to build these things, but different people who are maybe just vision researchers or NLP researchers who don't really want to necessarily deal with physical robots. And so there's this more general term, embodied AI, where I think of it being a little bit more inclusive, and we're perfectly potentially happy with just doing everything in simulation, but we're also happy with, showing that what the models that we trained in simulation works as well in the real world. But for all of this, what we start with is we want to have simulation frameworks that allow us to design the tasks and explore the problems that we want to explore, as well as having a set of data, 3D assets, different kind of episodes that we want to do, as well as from which we can then define very specific tasks like, we want to set a table, put the plates on the table, put the silverware around it, or do we want to do a different task, such as, move one object to another? And once we have all of this set up, then we can start to explore different approaches and compare them to see which one works better than other. So as I mentioned, I've worked, and this is also collaboration with a lot of other people, because building simulation environments is not easy. So I've been privileged to collaborate with different people from UCSD, from Facebook, and so forth, to build different simulation environments. And here I just show some snippets from two, Sapien and Habitat 2.0, and I highly recommend both. And so Sapien, it consists of two parts. One part is the actual simulation framework that allows a robot to interact with different objects, as well as a data set, the Habitat-Matterport data set, which consists of over 2,000 objects that has been annotated with their movement. And this basically is a step forward toward having this interactive vision robotics research that has a very diverse set of articulated assets. And so here's an example of a robot taking working in Sapien that's able to move pairs around and able to also, close and open drawers. And based on this framework, and also this is work actually from Hao Su's lab, UCSD. They've developed different challenges if you're interested in participating in the Manning Scale Challenge, which is so tomorrow, I will say tomorrow, there's this huge big embodied AI workshop that it's a whole day thing. You're all welcome to participate or to join, and then you can, take a look at all the different kind of challenges that are presented there. But the manual skill challenge focuses more on manipulation and being able to interact with different kinds of objects and to move things around. On the other side, I've also helped to work on Habitat 2.0, where it's basically a fast simulator that allows for interaction. And in order to allow for this, again, you need to have the assets, the scenes that allows for manipulation. And so there's a set of replica cat, it's a set of interactive scene layout that allows for people to interact with, and as well as a way to procedurally generate clutter. So you can, if you wanted to pick up a soda can, you want to have the soda can be placed in different things. And one of the highlights of this work is that it's just a very fast simulator. And in this initial work, again, we're focusing on rearrangement. In this initial work, we focus on rearrangement tasks where you can move objects from a specified initial position to target positions. But these are all specified via just their geometric coordinates. So here there's no language, but it does still require the robot to learn to chain different skills together. Like it has to move and navigate to somewhere, as well to be able to pick something up and then place it. And so here you can see it's going around, opening drawers and picking up this bowl and placing it away. Okay. And you can pick up different things. Yeah. And with this, then once you have this setup and once you have this framework, then you can start to compare, what methods works well. Is it a monolithic RL agent, which you train end to end, or is it something that maybe you a more modular approach where there's a component that does some task planning, and then maybe for each skills. So for instance, I mentioned that you need to be able to navigate from one point to another. You need to be able to pick up object and place object, and maybe you train a skill for each set. And so you train a neural network for each skill. And so here, this you don't need to pay too much attention to these graphs, but the main thing to say is that you can compare these approaches, and basically with monolithic RL, it often takes a lot of experience to train. And so far, in that plot, the robot that method is not as good as others. But that's not to say if you train further, it won't be as good. But overall, for these long horizon tasks where you have to do one thing and then another, you can see if you just do one action, it can be maybe even close to 100%, but as you do more and more, the errors compound and it's gonna drop off. And so the idea of these different simulation frameworks and these environments is that it allows you to do these different kind of tasks and to be able to compare. But in order to support all of this, one thing is very, very important. And I think this is something that we as a community have been starting to recognize its importance and starting to build more and more, which is data sets. And by data set, what I mean is these 3D assets that allow you to do these different interactions. So I've, again, worked with a lot of different people on a lot of different data sets. And so the latest of which is this a set of data called Habitat-Matterport 3D data set, or HM3D. And this is a fairly large scale set of data where we have where you have near complete reconstructions, and it's fairly high quality. And it is one of the largest ever data set of 3D reconstructed indoor spaces. We have over 1,000 high resolution 3D reconstructions, and they come from all over the world. And with so these reconstructions are multi-room reconstructions. So you'll see here that they have a large span of floor area as well as potentially multiple floors, and they have a variety of rooms. And this is just showing a 3D turntable of houses. In this CVPR, this is through a lot of manual effort. Basically, workers have semantically annotated this data set so that if you wanted to know where the bed was or the kitchen, now the semantic labels, and this is 3D semantics. And for this, this statistics may be a little bit out of date, but at one point there was only 200 or so scenes annotated and 3,000 rooms or so. And this took just tons of human effort. Yeah. More recently, we've been working on a synthetic data set. And why do we want to go for synthetic data set instead of going for this realistic semantic, like real world scans? The synthetic data set, what it allows for you to do is to have these different rearrangement of the rooms. And in addition, you'll notice that when we were looking at the scans, some of it, the scan quality may not be very good. It may be noisy, it may be very partial or incomplete. These synthetic data sets are very complete and high quality. And in addition, they allow for interaction. This particular one doesn't allow for interaction yet, but we do plan to have a support interaction as well. Interaction meaning that the cabinets can open and close. And this particular HSSD data set, we basically try to have it, it's connected from human designed scenes. And so the placement of object can match that of the real world, such as the HM3D SEM, much better than, say, something that's procedurally generated like Poxor. And in recent experiments, we actually can show that even a small quantity of these HSSD scenes, if you were to train an end-to-end RL agent that navigates to, say, a chair or a table, can work better when you take this pre-trained model on this small number of HSSD scenes and transfer that to, say, the HM3D data set. It can work much better than if you were to train with 1,000 Poxor or generated scenes. So there's value in having high quality data that match the real world. But okay, I'm gonna continue with more. What I said that we want synthetic scenes because you can interact with them. While with scanned scenes, it's very hard. But can we actually take scanned scenes and create these interactive environments as well? So this is an effort that took a number of years, and it was presented at New RIPS last year, where we built this, we took scans of the real world, and we annotated not just the semantics, but the articulation parameters so that you can create this environment that can, with these cabinets and drawers that can open and close. You will notice that this is actually also incomplete. So the next step will be to complete the geometry so that you can actually put things in the drawers. And to do so, we actually took a space and we would take multiple scans, and we would basically have, obviously each space has multiple objects, which we will semantically annotate, but we annotate not just at the object level, but at the part level, so that you can actually annotate that this drawer is supposed to move in and out. And with the multiple scans, we will also correspond which door is which across the two scans. So you have this, basically you have the same environment in two articulation states that you can see. And in addition, we also provide an oriented bounding box for each object, as well as the articulation parameters for all the parts. So we do hope this data set can be very useful for the robotics community to investigate robots that can manipulate objects based on real-world scans. Oops. In total, we've collected 108 environments, and these, again, if you count the number of objects, it's almost 10,000 objects with 4,000 or so parts. And here's just some more visualizations of the articulated objects moving in and out. And to do this, we basically created a pipeline for scanning and annotating. And I already told you about Dataset, and we also did some preliminary benchmarks for some tasks that could be of interest. Mainly, these are kind of, I would say, simple tasks such as object instance segmentation, part mobility. And we do plan to run a challenge in the future that will, and so if you're interested, look out for this. And so moving on to what else I think we need to get to intelligent home robots, it would be great if we can also have, so I've talked about having end-to-end RL methods, but I don't quite believe that's the way to go. So instead, I think it's important to have modular approaches. And whether there are subtasks that we can define and submodules that can be helpful as building blocks. So I've already kind of mentioned this, but I think one useful subtask would be to, take say a single view image or a multi-view image and be able to predict what the part and motion is. And this allows you to, if you are a robot, it allows you to maybe forecast how something could move when you open it, or if we're in the data creation regime, it will enable us to maybe potentially automatically create more of these interactive environments. And so some work that we did that was presented last year at ECCV, we would take a single view image and we would want to have as output for each part what kind of part it is, as well as the motion parameters, such as the type of motion, is it a rotation, is it a translation, the axis, and then for rotation, you also want an origin. And we focused on basically just only 3 different part types, like drawers, doors, and lids. And these are things that you can open. So we called our task the openable part detection. And to do this, we basically leverage 2, this is image-based data set, which we call OPD Sense and OPD Real. And the OPD Sense is synthetic object that's based on the partlet mobilities, while the OPD Real is single object with articulations that we captured with the MultiScan scanning pipeline. And in order to do, we propose 2 simple baselines for this task, which is basically a detect and predict strategy. We detect what parts there are and predict the motions. And what we do is we leverage existing instance segmentation networks, and we just add prediction heads for the motion prediction. And we use 2 popular instance segmentation models. One is mask-RCNN, and we would just add, we would basically try to predict the pose of the object and then the motion parameters, the axis, the type, and origin in kind of a canonical object coordinates. And we would do the same thing based on using mask-to-former as well. Add the different heads. And here are just some visualizations of the predictions. We do fairly well, but with the mask-to-former based method, it's able to be a bit more accurate. So here, what the numbers are is kind of the error that you would get. The other thing I'm interested in is doing more modular approaches to embodied AI. So beyond saying defining like what some good tasks there could be, we are also interested in saying, what should the architecture of the agent be? And to do this, I basically investigate. We first set up this. We set up this multi-object navigation. So it's kind of like the single object navigation, but we do, instead of navigating to just one object, we navigate to a sequence of objects. And part of the reason for this is that if you think about this initial thing, that video I showed of a agent that's going around and taking the stuffed animal from one place to another, it basically needed to go to 3 different objects in order. And so we can think of this task as basically the same task, but instead of you having to manipulate the object, you're just going to the different objects. And with this, It's
like, is that your meeting? Maybe you can unmute yourself.
Okay. Oh, sorry. Okay. Should I mute? Okay. Very tricky.
I think this one has an issue.
Oh. Should I mute myself?
Yes. I think maybe you should mute yourself and unmute myself. I think there's some issue with this, the microphone, this kind of tricky. Say something.
Hello. Just a little bit of echo. What if you just stop your speaker?
Actually, I already stopped. So actually, your voice comes through this one.
Okay.
Both.
You can show me to it. Somebody said the previous setting works fine.
Okay. Yeah, maybe let's just keep the previous. Because someone said in the room that like you're muted.
Oh, okay. It may be.
Okay.
Okay, sorry for the interruption.
Okay, I think it's working now. Okay, sure.
Okay, sorry for the interruption. I was talking about the semantic memory for embodied AI. So we initially proposed this multiple object navigation for 2 reasons. Again, one is that it's a simplified version of this, rearrangement where we, instead of having to pick up something and place it, all we needed to do is to go to the different objects in order. And here we actually, what you see here is actually a simplified version where we would actually not even go to real objects, but just inserted cylinders of different colors. And the other idea is that we wanted to propose, basically do systematic investigation of different map representations, because if you're just doing a single, navigating to a single object, maybe you don't need to remember anything else. You can just do it. While if you need to navigate to multiple objects, ideally you would want to go back to, if you've already seen the object that you need to go to. Okay. So based on that, we also developed a kind of a more modular approach. And before I go to the modular approach, let's just have some visuals of what this going to multiple object means. So basically we have a little robot. We want to go to object 1, and this is indicated by a one hot vector of this is the type of object you want to go to. And once it locates it, it's supposed to issue this found action. And then after that, it's told what object it needs to go to next. And so, and once it finds that, it says find, and then it goes on to this another object and so forth. And then you'll notice that here, there's also other cylinders that are not the yellow, the blue, and the white that it didn't need to go to. Those are kind of distractor objects where maybe it's good to keep track of them because it doesn't know exactly the colors it needs to go to, but it doesn't need to go to them in the end. Okay. And the action space that we looked at was basically being able to go forward by some amount, turn left, turn right, and then calling this found action. And like I said, we first proposed this in order to investigate memory and mapping. If we have a modular approach, then we can actually systematically explore the different modules. But let's first take a look at the memory and mapping. And so this initial work, we basically just was actually training end-to-end agents. And we wanted to see, okay, what happens if you have a map where you know everything, you know where things are, as well as knowing what object is at each position. You can also do a RNN, which doesn't have this spatial map, but it will accumulate memory of what has happened, as well as maybe a map where it's slowly revealed over time, but once you see something, you get the oracle information. And in contrast, you can also have this map where it's still GUID-based, but instead of storing the semantic label, you would project features into each GUID. Or you can also use those features potentially to be able to predict what object was at that location. So if we look at these different methods, so this is, I think, going for 3 different, going to 3 different objects. And you can see as you train more, with more training experience, all these methods improve, but it definitely helps to have a map. And of course, if you have the ground truth information, it's the best while if you need to predict what kind of things is there, it's less accurate. But I think what's more interesting is to see what happens after you find the first object. If you want to go to the second object, does it remember where it has gone, where it has seen the object and can accurately go back to it? And so for this, we kind of separate the case into 2. One is that the object was previously seen versus one it was not. And you can see if you had oracle information, it didn't really matter if it was seen or not. Like if you had oracle information of the whole map, complete map, it doesn't matter if it was seen or not, it would be able to, there's only a small improvement for things that has been seen before. But for these maps where you're learning and you're slowly, progressively revealed, then being able to build this map is very helpful, especially compared to something that just accumulates information in a non-spatial way. Okay, I think I have 5 minutes. I quickly go over this our modular approach. Our modular approach is that we're given the goal and the RGB and depth, and then we have a object detector that will tell me if the object is there, and then we slowly again accumulate information to our map, and we'll put information on, build it up. And then in addition, there's a component that decides, okay, do I need to explore or not? And if I explore, where should I go? And then this I call the planning component, but this is really basic. This is basic. If I have the object in my map, then I go to it. If not, then I pick whatever the exploration policy told me. And finally, we have this other module that will say, what action to take. And as I already mentioned, we can, if we have this modular approach, we can systematically study each component. And in general, it's good to be able to pre-train the different modules. And it's even better if our system can be tuned end to end. So I think the using of pre-trained models is not anything new. It's very commonly done for the object detection part. And what's slightly less common is potentially, using a pre-trained module for the navigation, but you could very easily put a pre-trained point nav agent in there, because what we're trying to do here in navigation is we're just saying, here we are, and this is the relative place we want to move to. And that really fits the point nav. And what we show is that you can do potentially much better. This is with the Oracle semantic map. With the point nav model, partly because it's much faster and it doesn't get stuck. Okay. And we have a challenge. So we are part of the CVPR Tomorrow's Embodied AI workshop. You should all come. Unfortunately, nobody participated in our challenge this time. Our focus is on small objects, so we place little objects on different things, but we'll keep our leaderboard open. So if you're interested in participating, please participate. And also the key is that if you participate and there's not that many people, you can, and if you get to be number one, you can present at the workshop, so there's it's better to participate in the less popular ones. So I don't know how many minutes I have, but I'll say that I want to advocate to the use of language for task specification. So large language models are very popular now. They can be a source of knowledge, and you can use these models to with language specification for perception, planning, and control. And people are doing this. I actually haven't done very much work in this, but other people are doing it. Perception, you can do like open vocabulary perception. Planning, you can maybe ask ChatGPT to help you break complex tasks down into subtasks. And control, you can actually generate programs that can control robots via API. Again, this is not my work, but this is just examples of people using language models for open vocabulary detection. And here's an example of me querying ChatGPT about how to set a table for 4. And maybe it's a little bit hard to understand what ChatGPT told me, but it seemed to know a lot. It says that robots need to gather all the materials first, that plates, utensils, glasses, and napkins. And then it says, you would place them around the table and so forth. So there's a lot of knowledge there. And I think this could be a very exciting direction. Again, not my work, but you can use these models for planning. You can, if you want to do, different, how do you brush teeth? How do you throw away paper? It'll give you step-by-step instructions. And yeah, and then this paper, do as I can, not as I say. I think it's I feel it's fairly famous, but maybe you guys haven't heard of it. I don't know, but it's from Google. It's basically saying how you can use language to basically figure out what's possible. It can give you a list of potential suggestions, and then you can use perception to say, okay, which of these actions can I actually do? And you can select from them. Okay, I'm pretty much at the end. So I opened this talk with a video of some robot going about and picking up a little stuffed animal. And this is part of the Home Robot Open Vocabulary Mobile Manipulation Challenge at NeurIPS 2023. And for this, we basically use the HSSD things that I introduced, as well as an object from a variety of different data sets. And the idea here is that what you want to do is you want to find some object and some start receptacle that's specified, and then you want to place it on some goal receptacle. And there's different variants where maybe the goal receptacle is not specified, so forth. And here's just a baseline. But this is a NeurIPS 2023 challenge, so you're all encouraged to participate and try out your nice method. And that's it for me. Yeah. Okay, repeat and say language. Okay. Thank you.
you have any questions? Actually, I can ask the first question. So actually, like one general question regarding like all this, like data set, synthetic data set, or like scan data set. What do you think is like the biggest difficulty that hinders from like model learned in this data set to apply them to the real world application? What do you think is the biggest gap, like the reality or the reality gap or the like the scale or all this stuff? Which one do you think is like the most difficult? Biggest gap?
I think it depends on exactly what you're doing. So I do think that each role. So maybe that question is kind of, I feel very general in the sense that there's, if I have a robot that's trained in synthetic data, then it may not work in the real world because maybe it's just noise. So one thing I will say is that some of what I've shown is that, noise-free environment. So in the real world, there's always noise, right? So that's one of the biggest gap. While in the synthetic world, you can simulate noise, but do you simulate, how exact do you need to simulate the noise? And what part of the noise is important? Do you simulate all the noise? That's one thing. And then there is also, depending on the modality you use, the sim to real gap can be either less or more. For instance, if you are in the synthetic world, if you use point clouds or depths, then there's less sim to real gap than if you were to use color. But maybe if you were able to randomize enough in the synthetic world, then you would be able to cover such a broad space that even so reality you didn't quite match, it's just a small subset, so maybe you're okay. Yeah, but you can go on and on here.
I have a question about the language model, using the language model to elaborate the sub-plans. So these language models are based on some common senses.
Yes.
But in some environment, this robot needs to interact with the environment in certain kinds, right? In that case, how can we deal with the situation that this common sense is not applied to this particular environment?
So maybe a couple of thoughts. One is that I think language models, you're right, it's just common sense, but I think we're just at the point where this is starting to be able to happen. So it's very exciting. So you should do it.
Right.
But for a specific environment, I think you still need to have perception in the sense that you can't just rely on common sense. You need to actually see what's actually going on. And that's where maybe perception is going, where you would use your perception to say, okay, usually, for instance, a mouse, usually most people are right-handed, so maybe the mouse is on the right hand of the thing, and you would use the right hand. That's where you would look for the mouse. But some people are left-handed, right? And maybe the mouse fell over, and you have to find it. And then so you need to use like the perception to actually figure out what's actually the state of the world. And in my mind, the language model maybe can help you, but maybe it's better if you can actually build a representation. I like structured representations. I actually like Andy's talk about maybe you have like graphs.
I guess my better question is whether we need to fine tune this large language models, or whether we need to get this basic common sense and combining with this perception and just generate something else with some other models or something. So I'm not very sure whether we have to fine tune it or we need to introduce new model to combine it with fusion. We don't know, right?
I can speculate a lot, but what I will say is that maybe this is why it's so exciting. You can go explore. And I suspect that you have to do fine tuning. You will have to do new modules. You will have to error correct. You will have to do everything. That's why this is just a lot of opportunities here.
Sure. Thank you.
Hi, Angel.
Hello.
That was a really delightful talk. Towards the end, you advocated, or I guess kind of throughout the talk, you advocated for using language as a way of sort of like specifying the tasks and kind of providing a natural input to these embodied agents. Where do you think we're at for in terms of the embodied agents communicating back to us in natural language and kind of improving the legibility of what they're doing through language. Are we ready for that? Is that
we are? So I will have two parts. One is that I think they are, because it's if you use ChatGPT, it's actually amazing what it can do, right? So I think maybe we are at the stage where we can actually have these things try to tell us what it's doing and why is it doing it. It probably won't make sense at this point, but I think that would make sense. That it will make sense as the next step to try. But I also, even so, I advocate for the use of language as an important like avenue to pursue and an important component. I do not actually believe that it should be the only one, in the sense that, you know, maybe I want to say, put the dishes there, and I want to gesture there, and I want to be able to point, you know. And similarly, if we talk about how the models communicating back to us, I think language is great. It should say, okay, I'm yes, for one thing, if you told it to put the dishes there, maybe it would be good if it said, yes, I will do it, versus, you know, maybe it's grinding away, but you don't know really what it'll do. So it would be very helpful if we can say, yes, I will put the dishes on the table, or it could also just point as well to say, yes, I will go put the dishes there. So it can combine. And also a robot, you can have other like visual outputs or whatever to show. It can show you the map it learned. It can show you on the map what it's gonna do. So there's other ways to augment its communications.
great? Thank you.
Hi, hello.
Hello.
Nice talk. I'm really fond of your work, since minus and all of the data sets that you are presented, and simulators. Just I want to know, from your perspective point of view, what are your opinion with respect to implicit representation for cities? From one side, we have this scan environments where it's coming from the RGBD sensor and we are aggregating the data. From the other side, we have the synthetic environments where we can have some manipulator or have some options. But we, as you mentioned, we lack of noise and the explicit reality. But we have also now this new version of a scene representation, this implicit representation. I could like to hear from you, your point of view about implicit representation for the same task of planning, control, and learning from there.
I guess here, I feel I'm not very qualified to answer the question very well. First of all, implicit, exactly what does that mean? It means different things, I feel, to different people, in the sense that, you know, maybe what it means is that you have a network that's predicting the, you know, sign distance function, let's call it, or you have a network that's predicting something, or maybe you have a latent representation. It's implicit, it's not, you know, explicit map representation, let's say. So I feel it's hard to, depending on exactly what you mean by implicit, the answer could be a bit different. But what I would say is, in general, you know, whatever representation is useful for the robot or the agent is good. You know, if from practice implicit representations work well, that's great. But at some point, we need to be able to understand what the robot is doing. We need to communicate with it. And that's where I think the more explicit representations are very helpful, where, for instance, you know, you have something that maybe it doesn't really have a map, but if it can have this explicit representation for map that it generates for me to look at, that I know I can understand what's going on there, versus whatever implicit things it's in the latent vectors. I'm now using implicit to mean, you know, say, latent vectors versus explicit maps. I don't know what's going on there. So yeah.
Oh, thank you.